Okay, good afternoon. Can you hear me okay? So I guess by this point you're probably tired of all these snow talks, but if you bear with me, there's one more. So I'm going to primarily focus on satellite snow data simulation, but blending with in situ to remove some of the biases. So just want to start with some quick background, trying to remind us why we want to do data simulation. So this is one of my favorite quotes by Dr. Box, which says, essentially all models are wrong, but some are useful. I think you cannot agree more with that. And I will argue the same applies to data. So they are all wrong, but they have useful information that we can use to help our users for decision-making processes. So the key is to use them wisely. Here's the role that data simulation comes to play. We have our prior information in the models, and then the key is to have some new information in the data relative to the model. So if your data does not provide new information relative to the model, so don't expect data simulation to do the magic trick for you. So the hope here is to, by combining them, we get some better analysis, hopefully lead to better forecasts. And in order to develop a syllogism with the operational hydrology, we think there are several perspectives that we can use to try to address this issue. This was discussed at our previous data simulation workshops. We actually now have an acronym for the data simulation effort associated with HEPEX, which is called DAFO, Data Simulation for Operation Hydrology and Water Management. So we'll continue to use this acronym as we move on. So these are the four major perspectives that we came up with, but there's other points that discussed in this paper published in HES 2012. So the first effort, at least we can do, is to bring the different data simulation community together to try to learn from each other. And we are doing that with our data simulation workshops each time. And then, you know, at least in the US, satellite data simulation for operational hydrology is still in its very infancy point at this time. And also, as Chris already showed, you know, when you do research, you improve the simulation, and you not necessarily will improve your forecast in operational mode. So that's what we are also struggling with. And then when we do research, we use automatic DA. Yeah, it updates for you automatically through the computing system. But in the US, operational forecast centers, they do DA manually by, you know, just changing some parameters or states on the fly, based on their expert knowledge or experiences, trying to get a better forecast. So our goal here is to use our automatic DA, trying to get the manual DA, but not replacing them at the moment. There is still a long way to go because the hydrologists forecasters, they do have value to add it to the forecast. So I'm going to focus on this satellite DA in this talk. And believe it or not, snow is very important for many people around the world. So you look at the map there, runoff is dominated by snow melt for a large part around the world. And it's a critical element of hydrological cycle. When snow is sitting on the ground, it affects the water energy balance exchanges with the atmosphere. So it's very critical there. And it's also a very sensitive indicator for the climate change. So when the temperature increases, you get less snow, and it also melts faster, and you don't have water in the summer most of the time. And Snow, from hydrologic forecasting point of view, is a very important initial condition. It's also important for weather climate prediction. So just an example, if you heard about the California drought that's going on right now, look at the snowpack for the last 3 snow seasons. It's very low, very below the average, and it leads to the drought in this summer. So a lot of wildfires and stuff compared to what's happening like 3 years ago. And another example with Colorado River in terms of drought, this is one of my study areas. You see how the water is declining over the years. And snow, surprisingly, is also linked to flooding. So especially when you have rain falling on snow. This kind of events, rain and snow events, with climate change, they're becoming more and more common. So you'll see more and more of this in the future. And when this rainfall and snow melts much faster, so you got a very quick runoff. This is one of the famous rain and snow event caused flooding in the Northwest area in the United States in 1996. And the damage was very huge there. When you look at the daily rainfall and snow melt at one of the snow test sites, it reaches 200 millimeters per day. So that's a huge amount of water to generate runoff. So as I mentioned, we need the good model to start with in order for data assimilation to work. So look at this during this rain and snow events. You see here we are looking at the melt factor derived from snow tail observations. If there is no rain, the snow melts much more slowly. But if there are rain snow events, they melt much more quickly. And the melt factor, which is a very important factor in a lot of the temperature index-based snow melt models. And if you look in the literature, the value ranges we're using is with the red box. They don't account for rain and snow events. They enhance the melt. And same with the physically distributed models. So if you look at, these are the results from the NL-2 models that people use, real analysis data people use a lot for like drought monitoring and stuff. So there's a big event, rainfall event has rain, and look at the snow tail side, the snow basically is gone in a couple of days, but for the models, they tend to stay there for a long time. So our models currently don't account for this kind of events. So in order to be able to forecast these events, like flooding caused by these events, we need to enhance our models. Also, hopefully with the satellite data, we should be able to detect whether this is happening or not. And then, as you know, there are lots of snow information out there. They are all not perfect. Each information has their own issues and errors and uncertainties associated with it. There are remote sensing products that we mentioned, and operational reanalysis products, and in situ data, etc. So, what we can do with snow. There were some discussions in the earlier part of this workshop that we can do hydrology. We can estimate precipitation from soil moisture measurements. Here we are trying to do it with snow, so doing hydrology backwards with snow measurements as well. So you can estimate precipitation over snow-covered land area, which is currently not measurable from space by the satellite missions. So you can use the passive microwave data. Use this basic water balance equation, try to figure out what's the precipitation out there. So there was a paper published by my colleague Yuqiong Liu on this journal. So just very recently. And additionally, we are also trying to use snow DA to initialize our numerical weather prediction models. So here, just to show you, we made 3 runs to produce the snow water equivalent analysis, with the open loop ROM, and then direct insertion of snow 3 data from satellite, and then also ensemble camera filtering. So, and then we use that to initialize the weather research forecasting model that's very popular in the US for numerical weather prediction. We do see some positive impacts from forecasts like temperature and wind, etc. So this is just the first 24 hours. So we didn't look into the longer lead times. Finally, getting into the flow prediction part with snow data assimilation. As we have already discussed, there are a lot of challenges, mostly because remote sensing data are not reliable at the moment, especially in complex terrains. So there are some opportunities out there that we can take, to deal with these issues. One of the popular methods, which is also used in soil moisture data assimilation, is to scale the satellite products to the model. And then you only assimilate the anomalies. But in that case, you need a very good model to start with. Otherwise, you're not ending up with any good results. And also, you can do data assimilation based on the radiance instead of the retrieved products. The issue there is that you introduce uncertainty into your radiance transfer model as well. So there's also an issue over there. And then currently, we think that the visible information of on snow is more reliable than the passive microwave data, although it does not measure the snow amount. It only tells you the snow cover extent. But you can integrate them together. Hopefully, you get a better product. And then in this case, what I'm going to focus on is the last point, which is to blend the satellite 3 measurements with in situ observation and then assimilate them into the models. So the algorithm that we used is also called optimal interpolation that Patricia introduced the other day. Although here we are not, our background is the satellite data, not the model. So the key here is the weight calculation. So you have to weight your station data very wisely in order to get any value out of them. So the cool thing about this method is that you can specify a error term here, and then you can actually make it dynamically and temporarily changing. So this to adapt to your approach. At the Lhasa Gallery, we have our in-house system, which is called information system, non-information system on this, which is a very flexible framework integrating all non-surface models and different satellite data sets and different data assimilation techniques, trying to produce better analysis and forecast. It can be run by itself offline or coupled to a weather forecast model. So we did some initial study for slow streamflow simulation over Alaska a couple of years ago, and it's published in this paper in 2003, where we assimilating both modest snow cover and also unsafe snow depth. And the unsafe snow depth, we apply the bath correction method that I just mentioned, using the station data from these stations. So I'm going to skip the slow evaluation and focus on the streamflow. Here we are looking at the monthly streamflow from US, compared to USGS, from different model runs also. And I just want to highlight a few things here. Surprisingly, we got the best results with snow cover assimilation, which is shown in red. Their observation is in red circle. So when we add the the slow cover, snow depth estimation, we see some improvement in some basins, but not often. So we forget about this one because it's a glacier-driven basin that our model doesn't really account for glaciers. So you don't want to. So data estimation won't change anything there. And the issue is that when we look at the first three gauges, the blue line, it's overestimating the flow, which is by from the simulating the satellite-based snow depth data. So we went back to our algorithm and tried to improve a few things. The first thing we did was to incorporate in the terrain aspect information. As you see in this, the picture, you have two slopes adjacent to each other, and one has snow, one has no snow. So the reason is that the aspect is different. One is the one without snow is south facing, and the one with snow is north facing. So this time we try to do the batch collection a little bit more wisely by using the aspect information, and then also additionally we incorporate the MODIS slow cover information into the batch collection process. Basically, when MODIS says no snow, we don't batch correct, or we just remove the snow from the passing microwave. Because the assumption here is that MODIS snow cover detection is better than the passing microwave, or more reliable. And we are doing a few other smaller things trying to improve the batch collection algorithm. So here is a case study looking at the Upper Colorado River Basin. We have lots of stations here that we can use for batch collection. There are primarily two kinds of stations: the GHCN, which is the global hydrological climate network, and they are all located mostly in low elevation areas. And then there's a snowtail network in the US that's primarily at high elevations. So it's good that we have stations from both high and low elevations for the batch collection. And so we're looking at 15 large river basins in this area. So the largest basin, it's more than 100,000 square miles, so it's huge. And because the basin is heavily regulated, so we cannot use the US Streamflow, so our model does not account for reservoir operations or regulations. So we use the monthly natural flow data from Bureau of Reclamation. So we blend the satellite data with in-situ observations and generate several products actually. So we can blend in the GHCN data with optimal interpolation, and we can also, at the same time, we can blend in the aspect information and produce two different products. And then additionally, we can blend in snowtail with or without the aspect information. And then finally, on top of that, we can try to examine whether MODIS slow cover bring in any additional information here. So there were 5 products. 4 of them did not use MODIS slow cover, and they found out that the last one that used MODIS slow cover. So here, for the first 4 data sets, we assimilate them into the model, and then we are comparing the slow cover from the model with MODIS. It's an independent evaluation because MODIS was not used in the first 4 products. As you see, we improved the probability of detection across the area. And the good thing is that we did not increase the false alarm ratio as well. So here it's just a seasonal cycle of POD and the FAR. Look at the higher elevation zone and the lower elevation zone for POD and the FAR. So POD smoothly increases, and we have negative FAR. This is relative to the open loop, by the way. So you see, you want basically one positive FAR, you want negative positive POD differences and negative FAR differences. But here we see some increases in force-alarm ratio actually. This is primarily due to the number of observations that go into this matrix. So during the end of the snow season, we really did not have much information observation to compute this matrix. So that's the reason over there. So for Streamflow evaluation, we were looking at primarily what we call the normalized information contribution for three metrics: the root mean square error, correlation, and natural cyclic efficiency. So basically, it's just taking the difference between the DA and the open loop and normalized by the open loop. So you'll be looking at the improvement from DA relative to the open loop. So if NIC is equal to 0, then there's basically no impact from DA. If it's greater than 0, it's positive impact from DA. And then the maximum, of course, is 1. You cannot get higher than 1. And then if it's a negative, and then you get negative impact from DA. So here we want to check the impact from incorporating the terrain aspect information and MODIS information. So the first bar, the white bar, is adding aspect information to the GHC with the GHC stations, like the lower elevation stations. So we didn't see much impact of aspect because at the lower elevations, where the snow is going to melt, the snow melt is going to be dominated by temperature. You know, it's not going to be the aspect is not having a huge impact there. But for higher elevations, where the snow tail sites are located, you see a huge impact from considering the aspect. So you got always positive influence from adding aspect information, and then on top of that, we got some some additional or marginal improvements from using MODIS flow cover information, which is shown in the green bars. So it looks like if we consider the aspect information at the snow tail sites and the MODIS flow cover, we are going to get the best overall best results. So here is a overall like summary of the Streamflow simulation. So we are looking at the scale score on root mean square error, National cyclic efficiency, and the correlation coefficient. So you see that in most of these 15 basins we get improvements, but a few of them we are not doing so well. Although we got improvement in the correlation, but not necessarily root mean square error. So, and when we go back to look at the station network, we realize that in these basins we don't have much. We don't have many stations available for, especially the snow tail sites. So snow tail sites are located in areas that there is snow. So if you don't have snow tail data, then the chances are that you're not going to get any improvement. So here we're looking at again the monthly mean flow comparisons. So for the 15 basins, when we consider aspect, we get a good agreement with observation, except for this a couple of basins where we don't have snow tail data. So the station coverage is really important here. So if you don't have stations located at high elevations, then you're not going to be able to bias correct your passive macro data. So we are not right at the moment. We are applying this methodology continentally over the coast region, continental United States. So we'll be looking at 31 years of data, 3 microwave sensors here, one after another, and then we'll be looking at the USGS daily streamflow data, but for very small basins, because the large basins are all regulated. And we'll also be looking at the natural flow data. We got some pretty interesting preliminary results on this, but For the interest of time, I'm not going to show them here. So some concluding remarks. In order for the passive microdata assimilation to be successful, we need a good, a reasonable, at least, model to start with, and we needed data sets that contains new information relative to the model. And then it looks like blending satellite data with in-situ observations can improve the Streamflow simulations. Although it's critical that you have good representation of the in terms of station network. But they don't need to be too dense, right? Otherwise, there's no need for the passive microdata. And also, it's important to consider the terrain aspect, which is having a large impact on the slow evolution. And then model slow cover can be used to provide some additional improvement. And then the ongoing work here is to extend this to the continental scale. We are also doing it with the U.S. Air Force Weather Agency. They want to apply to a global scale. But again, the results are going to heavily rely on the station network for this approach. And then, of course, to make it more relevant for operational forecasting, we need to implement the operational context and do the verification there. So just want to acknowledge my co-authors and funding agencies. I can take any questions if there's time.
Near the beginning of your talk, you mentioned the national is manual.
Yeah.
And it's a theme of a lot of the sessions has been that automatic data assimilation is good in theory, but not very good in practice.
Right.
Have people quantified the benefits of the manual data? Is that?
Oh yeah, they must work, otherwise they will not do it. Yeah, so I guess because the river forecast centers they are very local, so they know their area very well. So basically, they for example, at the time of forecast, they know how much snow is sitting on the ground just based on their experience, and they can change. They know what part of the model, like parameter, is not matching the situation right now. They can just go and adjust it, and that's how they do it. And until we show that there's concrete improvement from automatic DA at all times, at all locations, otherwise they will be hesitant to jump into the automatic DA.
Do we know what they know that the algorithm does?
I think they know that they are going to focus on why not that they are working, but why they're not working. So I guess I remember at one of the workshops we present this results, and one of the comments from Rob Hartman, who is a forecaster at California River Forecast Center. He said, well, you cannot compare to your model open loop. You should compare the results to what we have now. Because they believe they already have a very strong system, right? So I guess in order to show benefit, we have to start with what they have and be able to reproduce what they do manually in time, on the fly. And then we show benefits on top of that. So.
Thank you. Thank you very much.
Thank you.
I have two good news.